All right, let's get started. This is Dr. Spencer. I'm going to be going over a quick review of some big concepts from clinical pharmacokinetics. This is going to be pretty quick. I know you guys have got a lot of finals to study for, so this is really just some of the big concepts that I think you need to know and might be helpful for your exam. However, just a disclosure, I did not write your final exam, so please study more than just this, but I think this will help you. All right, so let's clear up some confusion about some infusions. When it comes to vancomycin and aminoglycoside dosing, my best advice to you is to review your T's. So this is going to be really important. I think you can pretty much get any of the calculations correct if you know what the T's stand for. So let's talk about the first T. This is T just by itself, and this is the time of infusion. So it's shown here in the red. And keep in mind that the time of infusion for aminoglycosides and vancomycin are different. For aminoglycosides, we see that the infusion time is about 30 minutes, and that's pretty standard time for infusion. But for vancomycin, this does vary. Oftentimes, it's going to be 2 hours. Many hospitals would do a blanket of 2 hours for the infusion. At University of Louisville Hospital, we do no more than a gram an hour. So if patients on a gram, they might get it infused over an hour. If they're on 2 grams, it's infused over 2 hours. But bottom line is, for vancomycin, that may vary from institution to institution. For aminoglycosides, it's pretty standard to be infused over 30 minutes. So T equals the time of infusion. All right, so this is T prime. This is the time between the end of the infusion and the peak, also referred to as the alpha phase. So this is shown here in the blue, and so keep in mind that after we get finished infusing the drug, it does require a little bit of time for it to distribute throughout the tissues. And at the end of the alpha phase, so right here at the end of this blue line, is when you would draw the peak. So for aminoglycosides, we allow about 30 minutes for distribution, or alpha phase, T prime, before we check the peak. For vancomycin, it's 1 hour. So these are pretty standard times. You need to know them. That's T prime. So, what about if you're asking, a lot of times you get a question from a nurse, like, when am I supposed to draw the peak? So this is where your T and your T prime come into play. So if you're thinking about the amount of time after you start the infusion to the time that you need to draw the peak, that's going to be your T, which is your time for infusion, plus your T prime. That's going to be the amount of time between the start of infusion and the peak. So for aminoglycosides, it's going to be 30 minutes plus 30 minutes equals 1 hour. So 30 minutes for the infusion, 30 minutes for the distribution or alpha phase, for a total of 1 hour. So for example, if we started an infusion at 10 o'clock of aminoglycosides, it would be finished infusing by 10:30, and you'd be ready to draw the peak at 11 o'clock. For vancomycin, again, it depends on how long the infusion may vary. The infusion time may vary, so either 1 hour or 2 hours. Here I've used the example of 2 hours for the infusion time, plus 1 hour to distribute equals a total of 3 hours. So if you were to start vancomycin at 10 a.m., then it would be finished infused by 12, and you would be able to check peak at 1 p.m. All right, final T, you're going to look at your tau. So that's your dosing interval. Remember that is, for example, Q8, Q12, Q24. So this is how often we are actually dosing the medication. This is referred to as tau. All right, so bottom line, know your T's, know that T, know that T, know that T, know Mr. T, know your T's. All right, so now moving on to beta-lactams. So we've got several different dosing options for beta-lactams. The first is intermittent dosing, and that's kind of more the conventional dosing. And then continuous infusion, and of course extended infusion. So Dr. Harding talked to you about all these. This slide should look familiar because I stole it from her. So let's talk first about intermittent dosing. All right, with this dosing option, we do have some time that it takes to get to steady state, so about 4 to 5, typically 5 to half lives to get to steady state. But then once we get to steady state, you can see that with intermittent dosing, we do have a true Cmax and Cmin, so maximum concentration and minimum concentration, because there will be some fluctuations in that concentration as the dose wears off. So we give a dose, the concentration's high, and then the drug is eliminated, and the concentration dips lower to the C-min. We give another dose, it goes up to the C-max, it dips lower to the C-min. So it continues this pattern while it's at steady state. So with the intermittent dosing, it's important to know that there is a actual C-max and C-min. With the continuous infusion, this is going to be different. We still have that time that it takes to get to steady state, but then once it's at steady state, there's really no C-max or C-min because the concentration should remain the same. So this is continuous infusion. We have no actual minimum concentration or maximum concentration. We have pretty much one steady concentration at steady state. All right, and then of course we have our extended infusion. So remember what Dr. Harding talked to you about with this. This is another dosing strategy where we can do extended infusion of beta-lactams. So typically the beta-lactams are infused over 30 minutes. And so with this extended infusion or prolonged infusion strategy, then we extend the infusion out from 30 minutes to about 3 hours, sometimes 4 hours. It kind of depends on the beta-lactam, but we have an extended infusion time. And so the point of this is to prolong that amount of time, that the percentage of time that the concentration is above the MIC. All right, so I touched on this a little bit on the previous slides, but remember that the time to steady state is going to be about 5 half-lives. And the thing for you to keep in mind is that this is very dependent on renal function. So think about the equation for T half-life. That's going to be 0.693 over K. So what is K? The elimination rate constant, which is extremely dependent on renal function because creatinine clearance is in the equation. So regardless of which drug you're dosing, whether it's vancomycin or aminoglycoside, so those Ks are listed here, the creatinine clearance does play a component. So the renal function, the bottom line here, is that the renal function plays a role in determining the T half-life and the time to steady state. So when you're looking at how long it's going to take to get to steady state, keep in mind that you're going to have to potentially do that T half-life equation, look at the K, look at the creatinine clearance, so make sure that you're able to do that. All right, so moving on to volume of distribution. This slide should look familiar to you. I stole it from Dr. Smith, and it has a couple factors that affect the distribution of drugs. So characteristics of the body's tissues. So think about, if you have a patient who is obese and has a high percentage of fat tissue, and you have a drug that's highly lipophilic or fat-loving, it is going to distribute very highly in that patient due to the high amount of fat tissue. So the characteristics of the body tissue is going to vary from person to person and thus affect the volume distribution. Other disease states such as CHF or ascites is going to change the amount of fluid potentially that you have, so the amount of water. So that's definitely going to affect the volume distribution. And, solubility, so how lipophilic or how hydrophilic, rather, is the medication. Is it going to be soluble in the water or is it not? Because that's going to affect, where it distributes to. And protein binding. So remember, if you have a drug that's very highly protein bound, it's more likely going to be found in the plasma because it's not going to be really crossing over in the tissue very much because it is bound to protein in the plasma. So that's where the drug's going to stay. All right, so thinking about loading doses, we don't always use loading doses with every medication, but they are particularly helpful, especially when you have drugs that have a high volume of distribution. So here's a quick little diagram for you all. So let's pretend that red square there is the blood or the bloodstream, and this little orange, salmony, peach color, whatever that is on the outside, that is going to be the tissue compartment. So let's say we have a drug that has a high volume of distribution. So we infuse that drug into the bloodstream. If it's just a maintenance dose, if it's a smaller dose, then what's going to happen is that we put that drug into the bloodstream, and if it has a high volume of distribution, it's going to distribute out into the tissues, leaving very little drug left in the bloodstream. So it may take several doses before we're actually able to have a high enough concentration in the bloodstream to really be therapeutic, because the first couple doses may be spent actually, distributing the drug into the tissue and not really leaving much of it in the bloodstream to be effective or therapeutic. So in drugs that have a high volume of distribution, sometimes it is helpful to give a loading dose. So in this situation, we're going to give a much bigger dose as a loading dose, and we're still going to have that same distribution into the tissues, but with the bigger dose, we're able to still distribute some drug into the tissues, but then leave a certain amount of drug in the bloodstream in order to be therapeutic and doing whatever it is that that drug is supposed to do. So that's the idea with loading doses, especially helpful for drugs that have a large volume of distribution. All right, so now let's talk about some drug interactions. So Dr. Risselman talked to you about the difference between drug interactions from a pharmacokinetic and pharmacodynamic standpoint. So let's start with talking about the pharmacokinetics. So remember that pharmacokinetics is what our body does to the drug. So this is your ADME, the whole absorption, distribution, metabolism, and excretion of the drug. So any type of interaction that interferes with one of these processes is going to be a pharmacokinetic type interaction. So the best example I can think of with this are going to be your CYP interactions, and a couple of people talked to you about CYP interactions. With Dr. Risselman, I know she mentioned the valproic acid and lamotrigine interaction. So with valproic acid, we see that there is an inhibition of lamotrigine metabolism. So that results in higher concentrations of lamotrigine. So the best dosing strategy for that would be to lower the dose of lamotrigine. And so I think you all did a practice problem about that, but that's definitely an example of a pharmacokinetic interaction. Some other ones that I can think about were listed in Dr. Malcolm's lecture. And so actually I've modified this chart a little bit more, added a couple things to it, but let's go through it there's a ton of examples here, but I'm just going to go through a couple of them. So for example, theophylline, which I know Dr. Smith talked to you about as well. We do have some inhibitors and inducers of theophylline. So for example, if you were to give phenytoin or broccoli, which is interesting. I mean, it's not even really technically a drug. That's a food. But either way, it's an inducer of CYP1A2. So we're going to induce theophylline, resulting in a decreased concentration of theophylline.